Welcome back. So in the last video on estimates, we talked about the fixed effects and the random effects and how to interpret those. Now we're going to get to the design effect and the ICC, as well as R squared and stuff like that. But before I explain any of this, there's an important topic that we need to understand called variance explained and what variance explained means. So it's best to start this out with a graphic. So look at this beautiful picture. Wow, we got motivation and weight loss and the relationship between the two. So that gray, black line, whatever it is, tells us what the mean of weight loss is. And so one of the questions that we very often ask in statistics is, why do these dots deviate from their mean? Why do some people lose more weight and why do other people lose less weight? And why do they deviate from the mean? As indicated by those red lines there. So like this dot right here has a huge discrepancy. So they lost about -8 pounds, or they gained 8 pounds. Why did they do that? Why weren't they closer to the mean? So when we are doing statistics, we are often interested in why do these people deviate from the mean? So one thing that we could do, one thing that we frequently do in statistics, is we add a predictor. And so notice when I add a predictor, in this case motivation, and we fit a regression line, which is indicated by the blue line there, we see that those deviations get smaller. So those residuals, for example, this one, it had a residual that looked like this, but now it looks like this. It got smaller. And so now we are able to explain why these dots deviated from their mean by adding a predictor. Or in other words, we have explained the variance. So we wanted to explain why people deviated from the mean. We included motivation as a predictor. When we did that, our residuals got smaller. And we measure the size of these residuals using what's called the variance. Now remember, the variance is equal to the standard deviation squared. So what we're trying to do in statistics is we are often trying to explain the variance or explain why people deviate from their mean. And we do that with predictors, as we saw in this example. So when we want to quantify how much smaller those residuals became, we can divide what they are now, or the variance of residuals after including motivation, divide that by what they were, or the variance of the residuals before motivation, or the variance of the residuals that use just the mean. And this ratio is called R squared, also known as variance explained. And again, because we're trying to explain why the variance got smaller. It got smaller because we added motivation. That's all. So that's regular regression. Now with mixed models, it gets a little more complicated, because we have two types of variance. So in this plot, we have ID on the x-axis and alcohol use on the y-axis, and the red line is the fixed effect, and the blue line is the random effect. And so we see two types of variance here. We see the variance of these gray dots from the blue dots, where the blue dot is each cluster ID's average. And then we have the variance of the blue dots from the red dots. So the first we call residual variance, and the second we call intercept variance. So when we're doing mixed models, there's something called total variance. So total variance, at least in this simple example, is made up of two components. The variance of each cluster mean from the fixed mean, which is the difference between the blue dots and the red dots, and the variance of each score from its cluster mean, which is the variance of the gray dots from the blue dots. Now remember this notation. Don't get scared, it's just math. Remember, Yij is equal to B0j plus E sub ij, and then B0j can be broken down into gamma 00 plus Uij. But if we were to combine both of those into one equation, we would get Yij is equal to gamma 00 plus Uij plus Eij. And so notice we have gamma 00, which is the fixed effect, and then we have two deviations, Uij and Eij. So Eij are each of the individual black dots from their blue dots, and then Uij are the blue dots deviating from the red dots. So mathematically, the total variance is equal to the variance of Uij plus the variance of Eij. In summary, there are variances from cluster means to fixed means, and there are variances from individual scores to the cluster means. And we can use that information to tell us some pretty cool things. So that brings us to the ICC, or the intra-class correlation, not the inter-class correlation. That's something different. It's the intra-class correlation. Mathematically, it's defined this way. It is the variance of uij, or the variance of the intercepts, divided by the variance of the intercepts plus the variance from the cluster means. Or another way to write it is the variance of the intercept divided by the total variance. So it measures the total variation that is due to cluster mean differences. So let's look at some visual examples. Let's say you have an ICC of 0. What would that look like? Well, it would look like this, where we have on the x-axis a bunch of different therapists. So these are the clusters, and then notice that the red lines and the blue lines overlap completely. Or in other words, there is no intercept variance. It is only residual variance that we have. And so because the numerator is 0, when we get 0 divided by whatever the residual variance is, we get an ICC of 0. In this case, if you have no intercept variance, there is no need for mixed models because there's no cluster level effects, or because knowing cluster doesn't help you identify differences in depression. Now let's look at a moderate ICC. Let's say our ICC is 0.53. What would that look like? So it would look like this. Again, we have therapists on the x-axis and depression scores on the y-axis, but notice now we have differences in means for each of the therapists. And if this is the case, we need mixed models because, again, therapist, or the ID, is giving us valuable information. It's telling us why people deviate in their intercepts. Or in other words, there are cluster level effects. And what about a 0.97 ICC? Well, here's a visual that looks like that. And notice that the deviation of the gray dots from the blue dots is much smaller than is the deviation of the blue dots from the red dots. And so that's why you get such a high ICC. And in this case, we definitely need mixed models. Why? Because there are massive cluster level intercept differences. So that's what the ICC is. It just tells you the proportion of the total variance in the model that is due to differences in cluster means. Now, there's also something that we call the design effect. So you remember back in the day, several videos ago, whatever that was, I said that independence is a really big deal. If you violate independence, it's really bad. And I said that if you violate independence, it's like you artificially inflate your sample size. And if you need a refresher on that idea, then I will link a video in the description. So what is the design effect? The design effect measures that precise value. The design effect tells us how much our sample is multiplied if we were to fail to use mixed models. So let's say our design effect is 2. What that means is that if we ignored the fact that we had clustered data, it would be the same as if we artificially doubled our sample size or multiplied our sample size by 2 if we ignore the dependencies in the data. And you know, there's some literature, and I remember I was taught this in grad school, that say that if the design effect is greater than 2, then you need mixed models. If it's less than 2, you don't need it. I don't know who came up with that idea, and I don't know why they said it. It doesn't make any sense. Any amount of doubling, like if it's 1.5, that's still multiplying my sample size by 1.5. That's a bad thing. You're gonna inflate your p-values, and you're gonna be making really misleading inferences. So I would just say, if the ICC is above 0, or if the design effect is above 1 by any degree, just use mixed models. So that covers the ICC and the design effect. Again, the ICC is a ratio of intercept variance to total variance, and the higher the ICC is, that means the more we need to use mixed models because the clusters have differences in intercept. Now we get into the final metric we're going to talk about, which is R-squared. And this is a tricky one and maybe a little controversial. I've seen some mixed model people say we should just abandon the idea of R-squared entirely. I don't know that I agree with that. I think it's kind of useful sometimes. But there are some caveats, which I'll talk about in a minute. Before we talk about R-squared, let me review. We have variances of clusters from their fixed means, and then we have variances of the individual scores from their cluster means. And so let's say we start with a baseline model. Or a baseline model means that we have no predictors other than estimating a mean for each of the clusters. And getting back to this idea of variance explained, we might want to be asking, why do the blue dots deviate from the red dots? In which case we're asking about intercept variance. Or we might ask, why do the black dots deviate from the blue dots? In which case we're asking about residual variance. And here's a visual of what that model would look like where we have no predictors. So again, you've seen these before. You've got the cluster variable on the x-axis and then the outcome on the y-axis. And so we might want to know, why do these black dots deviate from the blue dots, and why do these blue dots deviate from the red dots? Well, let's do as we did with simple regression and add a predictor. This time we're going to add socioeconomic status. And if we compute estimates and we look at the bottom, we get the R-squared estimates. And we get residual is 0.0592, and then the intercept is 0.439. What does that mean? Well, let's look at a visual again, because visuals are often the best way to understand things. So in this plot, we have SES on the x-axis, but I've labeled it, let's pretend I don't exist. In other words, we're not using SES as a predictor because we've got a baseline model. And if we look at math achievement, we could also plot the residuals. And so again, back to our question, why do these deviate from their cluster mean? Well, if I include SES, as in the plot on the right, we see that those residuals got a bit smaller. And so what is that R squared telling you, that 0.059 telling you? It is telling you the degree to which they got smaller from the model on the left to the model on the right. So when we add a predictor, it helps us reduce the size of our residuals, or it helps explain why these black dots deviate from their red line, because we got a new red line now that has SES, where it says, yay, I've been noticed. Now, what about intercept variance? Well, a visual that might help is to do something similar to what we did before. We have SES on the x-axis. Again, I'm pretending it doesn't exist. And we see the deviations of the intercepts from the fixed effect. And again, we want to know, why do these clusters differ from the fixed effect? And if we were to include SES, it's a little bit harder to visualize. We can see that the intercept differences are a little bit smaller relative to what they were before. I feel it my duty as a statistician to warn you and give you fair warning and warn you and stuff that sometimes R squared actually gets larger. So let's look at an example. Let's say that the red dots represent G1 or group 1 or cluster 1, and then the blue dots represent a different cluster. If you were to ignore the X predictor, notice that those two lines overlap perfectly. Or in other words, there is no intercept variance whatsoever in this specific case. But the minute we introduce a predictor, X, and use that predictor, notice what happens to the intercept. They get larger in their variances. So they had no difference before, but now they have a larger difference. And so that's why it's a little troublesome when you do mixed models, is that sometimes including a predictor actually makes the variance get smaller. So in this case, it's kind of a trade-off, that you get much smaller to the individual dots, but the intercept variance gets larger. And that's why you probably shouldn't interpret negative R squares. Doesn't mean that your model fits worse now, it just means that you've traded one kind of variance for the other kind of variance. So now let's look at all the estimates together. So the fixed effects, again, we interpret these just like we would in regression. So the intercept says that if SES is equal to 0, we expect your math achievement score to be 12.665. And for every 1 point change in socioeconomic status, we expect your math achievement score to go up 2.39 points. And then we also got the random effect. So the average deviation of the intercept is equal to 2.19. The average difference in slopes is equal to 0.64. And then the average deviation from each individual dot to its cluster mean is equal to 6.0688. And then our design effect, ICC, is 0.18. So nearly 20% of the variance is due to intercept differences. And the design effect is 8.91, which means if you were to ignore the clustering, it would be as if you duplicated your data almost 9 times and then analyzed it as if the data were independent, which would be a very bad thing to do. And then when we look at R squared, we see that when we add socioeconomic status, we reduce the residual variance by about 6%, and we reduce the intercept variance by almost 44%. So that covers Variance Explained. And as I've said repeatedly, and I will continue to say so, if you need extra help beyond what this YouTube video can provide, if you want quizzes, discussion boards, live interaction with me, please sign up for my live or my self-guided course on mixed modeling at simplistics.net and really take your education to the next level. Woo! And with that, let me review our learning objectives. Know what Variance Explained means. It's again, we're trying to figure out why scores deviate from their means. Also know why Variance Explained is more complicated with mixed models, and that's just because you have 2 sources of variance. You have the variance of the dots from their cluster means, and then the variance of the cluster means from the fixed effect means. Know what the ICC tells you. It tells you what proportion of the total variance is due to cluster level effects, or due to intercept differences. Know what the design effect tells you. It just tells you how much you would be artificially inflating your sample size if you were to ignore the fact that you have non-independent data. Rule of thumb for design effects. I think rules of thumb are dumb. So I don't care what people say about design effects of greater than 2. Yeah, if there's any design effect other than basically 1, you should do mixed models. And then also why R squared is more complicated with mixed models. Well, it kind of goes back to why variance explained is more complicated. With R squared, in addition to the fact that you have multiple sources of variance, multiple R squares, you can also get negative R squares. Yeah, and that's all I got for this video. In the next video, we're gonna be talking about model comparison. So I'll see you then. Peace out.